We'd finished up with degrees of freedom, right? Yeah. So we've talked about kind of this idea. Degrees of freedom are kind of a conceptually difficult thing to kind of put together, but again, the idea being we, in the calculation of parameters, we get to a point if everything needs to sum to zero where we get to a certain number of parameters that are fixed and not free to vary. This has implications for your statistical analysis. So just generally, because sometimes we don't talk about degrees of freedom a whole lot, so it's just kind of a mysterious thing that is correlated like 0.99 with your sample size, but things start to get a little bit more complicated once we get into like ANOVA designs and things along those lines. So other thing about p-values, okay? Again, just a refresher, p-value being the probability under sort of assuming the null hypotheses, right? When we say the probability under a specified statistical model, the specified statistical model is the null hypothesis, right? Assuming the null hypotheses, assuming that there's no difference or there's no effect, our p-value gives us the probability of selecting a sample having an observed value this extreme or more extreme, okay? So again, starts to get at how incompatible our data, the data that you've got, are with the null model, right? But what it doesn't do, doesn't tell us the truth of the null hypotheses. It doesn't indicate an effect size, and it doesn't alone give us strong evidence for much of anything outside of assuming that the null hypothesis is true. How likely would it be for us to select a sample of this extreme or more, right? But again, going back through with the whole procedure of null hypothesis testing, this starts to break down, given that this actually isn't the question we're asking. It's like you're asking your friend one thing, and then they give you an answer to a different question. It seems like it would be related, but it's not exactly what you wanted to get, right? That's kind of what's going on with this. We have to be very careful when we're making interpretations about p-values, okay? Now, for up to this point, what we've been doing is we've been, with our single sample with our z-test, right? What we've been doing is we've said, all right, here is our z-curve, here is our test statistic. I find a z-value that's right here. This is, say, 1.96 is my critical value that gets 0.25 and 0.25, or excuse me, 0.025 and 0.025 in either one of the tail on the two-tailed test. But what I've done is I've found a z-score here of, say, 2.5, and I go through and find a z-score of 2.5 in my table and find out sort of in the smaller portion what the probability value it would be of getting a z-score of 2.5 or above, right? And we just find that from our z-table, okay? People, we're on the same page? Okay. When we start to get into our t-tests, your t-test won't, or your t-table won't have a specific probability value for every test statistic that you have. That would just be a lot of tabling and intense kind of stuff. We're going to use an online calculator to get specific p-values. But what's important is that if we're going through and we're making a two-tailed test, okay, what we're saying is we want to know sort of on the high end or the small end what the probability is of obtaining a score of this amount or higher, right? And for our two-tailed tests, right, depending on whether or not we do this or do this, is going to give us a positive or a negative sort of value, right? So this, if we get something that's bigger, this will give us a positive value. This will give us a negative value. And what you'll see is the sign of these tests is largely arbitrary, at least in function, right? And so what we want to do with a two-tailed test, what we do when we go through and we find that probability value, what we would want to do is double that, right? So technically, what we've been doing up to this point, when we say, all right, I found a test statistic of 2.5. what I'm going to do is I'm going to go down through and I'm going to look in my Z table and I'm going to find the probability associated with having sort of what proportion of the distribution exceeds is at 2.5 or above, okay? And then I get that probability value. Technically, that's a one-tailed test, okay? Because we've completely ignored anything down here, right? If we're running a two-tailed test, what we would need to do is we need to find this value, and then we would need to double it, okay? Because again, what we're doing is we're looking at critical portions at the front end and at the high end and the bottom end. Because we're running a two-tailed test, what we need to do to get our specific value for the p-value for the two-tailed test is double that double that value. Okay, and so this becomes kind of automatic when we're running through and doing some of the analyses that with the computer system and things like that. We just understand this is where this is coming from, right? And so if you were to, let's say, running a t-test, right, and you go through and you get your critical value is 2.01, and you actually find your test statistic is actually exactly 2.01. So you say, all right, here, right? So what this is doing, and so that you say my p-value is equal 0.05, right? That's saying that there's 0.025 or 2.5% of the distribution up here, but also 2.5 end of the distribution up here. This p-value is going to change whether or not we're talking about a one-tailed or a two-tailed test. Okay. And we'll go through examples. I don't think I'm going to have you do any one-tailed test, but again, like we went through and talked about, I think last time, sort of this idea of, from a methodological standpoint, the one-tailed test is, there are lots of arguments for it. We don't actually do it in practice because of the potential for shenanigans and stuff like that. People saying, oh yeah, no, this is for sure. I sort of, even though this hypothesis would be counter to anything that's ever been done in the literature, I alone sort of predicted this in the correct direction, and so it turns out that I'm right with my one-tailed test. Questions on this? Okay. This link right here to this GraphPad calculator, this is a fantastic tool. Bookmark this in your web browser, on your laptops, things along those lines. This is a nice, basically what we can do here. What it looks like, right? And so if I would need to find, so my test statistic is 1.96 for a z-test here, and I calculate 1 point, so what's this? For a two-tailed test, it's p equals 0.05, right? And we knew this because that's our test statistic, right? But let's say I wanted to know what my p-value for a two-tailed test, if I had a z-value of 2.38, right? For a two-tailed test, it's going to be 0.0173, okay? Now, if I wanted to know what the probability of, if I want to turn that into a one-tailed test, I could just divide this. I could go 0.0173, and I divide that by 2. I'm going to get 0.009, right? So basically that's saying for a z-value of 2.38, the proportion of area under the curve beyond 2.38 just for one side is going to be 0.009, right? But because we're running a two-tailed test, we have to double that, which gives us our two-tailed tests here, okay? Same thing for our t statistic. Let's say I've got a t-test of 2.93 with 18 degrees of freedom, right? It's going to give me my p-value. It looks like again it's 0.009, right? So this is a very handy tool to be able to go through and start calculating. So we got calculate p-values for t statistics, f statistics, correlations, chi-squares. This is just a nice tool that I've found to be reliable and useful. So, and this will come in handy as you're working through some different sets. Okay. Questions on this? All right. So, jumping in. So we had talked about our t-testing, sort of using our t-distribution, because when we go through and we sample or substitute our population variance for our sample variance, right? The distribution of our test statistic no longer falls on a nice z-curve. But fortunately, it does fall on a nice set of curves. It falls on t-curves, right? And so t-curves are a family of curves based on the shape of the t-curve. Distribution of the test statistic is based on the number of degrees of freedom. As our degrees of freedom get very small, right, it gets pretty peaked. The distribution gets pretty peaked. It has some kind of thick, flat tails. As our degrees of freedom start to get larger and larger, it turns into a nice normal curve, right? But in this example, so we have, again, the librarian, a local library claims that on average books are 20 years old. So we have a student randomly selects 30 books and records the publication date for each. Sample has an average age of 23.8 years and a sample variance of 67.5. Okay, so we did a previous example like this, right? But we just had a population variance, right? And if we got that, then it's easy. We just run a z, right? Here, this is a much more realistic example where we don't have the population variance, right? And so what we're going to do is we're going to say, all right, I've got sample size is 30. My null hypothesis is that the population of books is going to equal, or I guess, okay, in the sentence state the, I'm getting ahead of myself here. All right, let's get our statistics up here. So sample size is 30. Mean has an average age of what? 23.8. And what is our variability estimate?
67.
Okay. And what is this? Is this variance or standard deviation? Yeah. Variance, right? Want to make sure you don't get those screwed up. I'm going to throw you curveballs from time to time. If you use a variance like a standard deviation, your test statistics are going to be really tiny, right? Because we need to go through and do some stuff in order to get our standard deviation here. Okay. So in a sentence, state the null hypothesis being tested. John, can you give me a statement on the null hypothesis here?
That the average age of the books in the library would be 20 years old.
Okay, yeah. So, and again, just want to make sure that you've specified this. This is kind of an example where the books in the library is the population, right? But if you're going through and reporting this, make sure that you let me know that you know that what population you're talking about, right? So the word population should probably, in your statement or null hypotheses, the word population should probably be in there somewhere, okay? So the null and alternative hypotheses using symbols. So we see mean age of books is 20 for a two-tailed test. Mean age of books is not equal 20, right? It's like, I don't know what it is. It's just something above or below 20 years, okay? So next thing we want to do is calculate 95% confidence interval for the point estimates of book age based on this sample. So what do I need to get first? Layla, to calculate my confidence interval.
I was just wondering if you would put the mean, the sample mean, or the 20 years.
Okay, which is it? What are we generating a confidence interval around? Nick?
No population parameter.
Well, we're trying to get the population parameter, but what value, what mean value goes into our confidence intervals? Is it going to be 20 or is it going to be 23.8?
23.8.
23.8. Because sort of my null value is 20, but what I've actually found, my best guess for the actual age of the population of books is 23.8, right? Now that's a different number than 20. What I don't know is whether or not this is sort of, if there's a difference because 20 is not a plausible value for the actual population, age of the population of books, or if this is just, my sample is just off by about 4 years, right? But what do I need? What do I need to calculate first before I, in order to calculate my confidence interval?
Would we need to know the degrees of freedom?
Well, we're going to need to know degrees of freedom, but before we even get to that point, what are we going to do? What are we going to calculate? What's that?
Standard error?
My standard error, right? So my standard error here, right, is going to be so 67.5 over my sample size 30. All right. Now I'm going to go through and just do that. Why did I do that? Because I'm working with a variance, right? This is just a shortcut, right? So what is my standard error here? What is it? 1.5?
Yep.
1.5 what? So you're gonna remember, at this stage, we're carrying things out 3 decimal places.
0, 0.
Oh, 1.5 is, okay.
Yeah.
Okay, fair enough. All right, so this is my standard error, okay? So I'm gonna go through in this, I'm gonna say 95% CI is gonna be, my point estimate is 23.8, plus or minus, but now what do I need? I need a critical value, right? And so what do I use for my critical value? Yeah, now I need to know my degrees of freedom, right? And for a one-tailed test, what are my degrees of freedom equal to? Do you remember? N minus 1, right? So if my sample size is 30, my degrees of freedom here is 29. Right? So, someone tell me, at a 95%, so alpha equal 0.05, what's going to be my critical value for a T distribution for a two-tailed test with 29 degrees of freedom? What do you got, Laura? Or, so, look at Laura up and then Layla. Laura, you will hit L's.
2.045.
2.045? Is that what other people got?
Yes. Yeah.
Okay, cool, right? So we can start to see, right, what would be my critical value if I was using a Z distribution? Okay, 1.96, right? 2.045 is somewhat higher than that, right? But again, because we're not using our population estimate, we're using a sample, right? And we got a pretty modest sample here too. And so the benchmarks, my critical value that I need to, that my test statistic needs to exceed within my t-test is larger than it would be, than what we would need to get with our z-test. Okay. Can you tell me what would be, what would my critical value be if my degrees of freedom were 50? 2.009, right? So again, as my degrees of freedom go up, as my sample size increases, the threshold that I need to reach in order to claim statistical significance gets smaller and smaller. And if we go and take a look at the bottom of your t-table, at some point you get infinity, and for infinity degrees of freedom, Evelina, what is my critical value? 1.96, right? Because as our test statistics start to get larger, or as our samples get larger and larger, basically our t-distribution basically approximates a normal distribution. Yeah.
You just said that as our degrees of freedom increase, our threshold for significance gets lower. Is that what Neil was talking about?
Neil's talking about a little bit different thing. Neil's not talking about our criteria for our test statistic. Neil's more talking about your standard error, right? what happens next to my standard error if I have 1,000 people in this sample?
Goes down.
It goes way down, right? What if I have 10? And that might be a difference of 3 days, right? But it's going to be statistically not 20 years. It's 20 years in 3 days, right? And so this is what Neil's talking about: is as our sample size increases, if I get enough people, if I have enough people in my sample, any observed difference is going to be statistically different, right? So as our estimates get more and more precise, it just makes it easier to say that things are statistically different, even when that difference might not be something that's actually a meaningful difference, right? Do we really care if the average age of the book is 20 years or 20 years and 3 days? Probably not. But I can force that to statistical significance if I get enough books in my sample. Okay. So this is another thing. This is sort of maybe a ways out, but at some point you'll see within certain types of statistics that people just use a critical value of 2, right? In terms of this T distribution. Again, this is this is common within the SEM literature and things along those lines. And a lot of programs will just use sort of a test statistic of 2 as sort of the cut point value. That's because if you're using SEM, you should have a large sample, and at that point, critical values technically 1.96, which is functionally 2. And so if you see in literature people talking about critical or test statistic exceeds 2, this is what they're talking about. This is where this is all coming from. Okay. All right, but we won't do that. We'll be more specific for the types of means-based analysis that you're doing. You probably just can't say, oh, this is above 2 or whatever, because there's going to be cases. Technically, if you have a test statistic of 2 in this scenario, you haven't achieved statistical significance. You're just right below it. Okay. So, someone tell me. So we got all the so 2.045 times 1.5 is going to be our standard error. Someone tell me what my interval estimate is here. What is it?
I got a
20.733
and 26.867.
26.867. Okay. Cool. Other people get that? Who else calculated this? Evelyn, you got it? Cool. We got a motion and a second. We're going to call it good. All right. People see, again, same structure, same thing we were doing before. Really, the only thing different that we're going to need to get is degrees of freedom based on our sample statistic and our new critical value here. People comfortable with this? Okay. Emilio, give me an interpretation of this confidence interval.
Any mean value that we, with the present data, any value that falls between that
7, yeah.
20.7 and 26.89 would be reasonable values. Any values that fall without it would be unreasonable.
Reasonable values for what?
The mean age of the books.
In the population of books in the library, right? Okay. So wanting to pull this all together. Again, once you start to get the hang of it, it starts to kind of make some sense, right? So we're saying, based on the data that we've collected, and assuming that we've got a random sample of books in the library, right? This could be a reasonable thing we could do, right? We say our best guess for the average age of the population of books is going to be 23.8, but values, sort of estimates, sort of lower bound for that age, the actual age in books is going to be 20.7, 26.9 is going to be the sort of high point. Values falling outside of that are going to be relatively inconsistent with the data that we've collected. Not impossible, but implausible and not consistent with the model that we created here. Okay. So again, Emilio, so the last data point says that we're going to conduct a hypothesis test. What do we already know before we even jump into this piece of it?
I mean, our values do include that the population mean, so that 20. So I mean,
well, does our interval estimate contain population mean of 20?
I mean slightly over, but so it would be closer to 21. So
Okay.
it should be close to that 0.05.
Is 20 in this interval? No, right? So what do we already know about our hypothesis test? What are we gonna do with it?
We're gonna reject.
We're gonna reject, right? Before I even go through and do my hypothesis test, I already know I'm gonna reject the null hypotheses. 20 is not in the span of 20.7 to 26.9, right? 20 is outside of that, right? So our value under the null is not consistent with the data that we've collected, right? And so when we go through and we run our hypothesis test, I already know based on my confidence interval that I'm going to reject the null hypothesis. Because if I wasn't, 20 would be in there. It's not. So I already know that, right? And so the hypothesis test is a foregone conclusion. I'm just doing this because, and like literally, I thought like, sort of at one point, maybe I'll just teach this whole entire sequence and never have you calculate a p-value. Maybe we'll just do interval estimates across the board. I didn't do that because you have to calculate p-values, like those are the rules of the game, right? But the point that I'm trying to make here is that there's nothing in that hypothesis test that you're going to get outside of a specific p-value that you don't already know based on your interval estimate, right? And so when you're going through and incorporating things, it starts to get tricky because you wouldn't want to say, oh, and then the hypothesis provides additional evidence that the actual mean age of books is probably greater than 20 because our hypothesis tests reject the null hypotheses. Well, we already knew that because we just calculated the confidence interval. Confidence interval doesn't contain 20, so I already know I'm going to reject the null hypothesis, right? You're right, I mean, it just barely misses it. It's close, right? And so we would say, not a huge difference maybe, right? But at least for the purposes of our up and down decision here, we already know that we're going to reject the null, okay? So let's go through and do that. So what do we need to do? So remember, our t-test is going to be our mean value minus what we expect under the null divided by our standard error, right? But we already got most of this stuff because we just calculated it all, right? Evelina, what's my point estimate?
23.8.
Oops, 23.8. And what's my null value? 20. And what's my standard error?
1.5.
1.5. Right, what's my t statistic? 2.533. 2.533? Okay. 2.533. What is my t critical? Nope.
2.045.
I'm sorry, what was it?
2.045.
2.045. Right? And so, if we were to go through and sort of draw our distribution, we see t equals 2.045 is our critical value. Here, we've got 2.533. It's actually farther down here. Let's see here, right? And so we would say that we would go through and we would reject the null hypothesis, right? But we already knew that. We already knew we were going to do that. If we want, the only thing that we're going to get with our t statistic is if we go and we say punch in 2.533, because 2.533 is in a t-value in your table, right? So you can't just look at that. But how many degrees of freedom do we have here? 29 degrees of freedom. Calculate our p-value. Gives us a p-value equal to 0.017. Okay. So again, this is our p-value for a two-tailed test because it was a non-directional test. And so we said part of this is above, part of this is below. When we're calculating our p-value says, well, what's the probability of obtaining a test statistic greater than plus or minus 2.533? We're getting both tails of the test, right? If I want to do a one-tailed test, I would take that p-value of 0.017 and I would divide it by 2. Gives me a 0.009 functionally, right? And so the proportion of the distribution, or the proportion of the distribution, or the proportion of the distribution that falls outside of 2.533 at the high end is going to be 0.009, right? But what we need to do is double that, and that's where we're getting sort of the upper and lower. So again, we go through, and based on our hypotheses test, we reject the null hypotheses, but we already knew that based on our confidence interval, right? As long as our confidence interval is conducted at the same alpha level as our statistical test, everything's gonna match up. Now, if that was a 95 and this was 99, or that was calculated our confidence interval at alpha equal 0.05, and this set our limit at alpha equal 0.01, then we could get differences, right? But we're using different benchmarks here. Okay. So again, this is why methodologists will say, so this is fine. This tells us up or down. You know, do we reject or fail to reject the null hypotheses? But our confidence interval did more than that because it told us how precise our estimate was and gave us a range of values that will be reasonable in terms of what the actual average age of books is in this library. Okay. People have questions? Yeah.
Kind of a question.
Yeah.
Just to clarify, so the Z-table assumes we're just doing the one-tailed test?
Yeah, for the most part, don't worry about Z.
Okay.
For the purposes of what we're going to do, you'll be done with Z tests after this set.
Okay.
And it's rare, not impossible, but rare to encounter a situation in applied science or applied statistics, at least with the stuff that we do, where we would do a Z test. Because again, to do a Z test, I need to do the population mean, and I need to know population or the mean of the reference population and the standard deviation of the reference population, which we almost never know, right? So Z is a nice introduction into the type of things we do, but T-distribution is going to be, for the most part, what we're working with.
Okay.
Other questions? Okay, cool. All right. So we've got our test statistics, we've got our confidence intervals, things along these lines. So confidence intervals are kind of one milestone, sort of hopefully you'll master, not hopefully, you will all be masters of the confidence interval by the time the year's up. You'll also be masters of the effect size, okay? If we're talking about effect size, we're talking about some estimate of the absolute magnitude of an effect in the population, okay? It's independent of sample size, right? We just talked, right? And so this is one of Neil's arguments that in physics, right, as my methods get increasingly precise, my ability to sort of reject the null hypotheses or sort of find evidence for my theory gets harder and harder and harder and harder, right? As I can go through and run out my equations to 10 decimal places, and I have infinitely precise ways of measuring something, right? It's not like, oh, I'm sort of within rounding error of my theory. It's either you're on your theory or you're not on your theory, right? And so as measurements get more precise in hard sciences, it starts to become increasingly difficult to provide evidence for your hypotheses, right? In our science, though, as our measures get better and better and increasingly more precise, the way we've set things up, it gets increasingly easy to say, oh yeah, there's to reject the null hypotheses, right? If I say that there's a relation between hair color and longevity, I just need to go through and get enough people until that correlation becomes significant, because it's probably not exactly 0, right? And so what ends up happening is, particularly if we've got very large studies, right, where we have these incredibly small p-values, probably what's driving that incredibly small p-value, at least some of the time? Laura?
Large sample size.
The large sample size, right? So if I have two situations, in one case I've got a correlation of 0.2 and another correlation of 0.2, is that correlation of 0.2 statistically significant? I don't know, depends on how many people I have. If I've got 15 people, no. If I've got 50 people, or sort of 200 people, probably, right? And so our effect sizes start to give us an idea of the magnitude of a difference independent of sample size, okay? So we're taking sort of this idea of hypothesis testing, setting it aside and saying, what is our estimate of the absolute magnitude of the difference, the relation, and coming up with a metric for going through and doing that, right? This is also important too, for small samples, right? I find a correlation of 0.3 in my study, but it's not statistically significant, right? Well, correlation in and of itself is a measure of effect size. Correlation of 0.3 is a medium effect size, right? So if I have evidence of a medium effect, I can say, well, I failed to reject in all hypotheses, but I got a really small sample. This was all the people I could get. If I look at my effect size, they actually suggest that there's probably nothing there. Can't make can't make too many inferences about it, right? But it suggests that there's something there that's worth pursuing, right? Because I found a medium effect, right? So augmenting our analyses with effect sizes start to become important because it starts to give us a sense for sort of how much of a difference or sort of the magnitude of some type of effect within the population. Okay. So again, like any other statistic, our effect size is an estimate of the population value. Okay. It's a point estimate, just like our means are point estimates, right? It's not going to be perfect. It's going to be off. We're going to get into the next unit talking about calculating confidence intervals around our effect sizes. That's a little bit complicated for a couple of different reasons, but know that my effect size for any given study is just a point estimate of the true population effect. Okay? And again, given what we talked about before on our approach to publishing and approach to science, what do we know about effect sizes in our current literature? Any guesses? Yeah?
That we can't use it alone, like we have to use it in combination with other.
Yeah. So we want to incorporate everything. What about so if I go through and I pull an effect size out of published peer-reviewed research articles, is that effect size likely to overestimate or underestimate the population value? Overestimate. Why is that? Do we publish things that have significant findings or not significant findings? Significant findings, right?
So
And-
usually the ones that are just average are gonna get
Yeah, right? So let's say, again, remembering that effect sizes also have a distribution, right? Actually, it's a skewed distribution, that causes some problems, but let's say that this is a distribution of effect sizes. And let's say my true effect is something that's small, right? If I have a small effect size, how many people do I need to have in my sample in order to identify a small effect? Lots, right? We usually don't have lots. We usually have a low amount. And so if I do find this effect, it might be an effect that's out here, right? Something that I can get, that I was able to find with my modest sample. I just happened to pull a sample that sort of was at this end of the distribution, and then I published this. But this is the only study that's been published, so everybody thinks we're looking for a medium effect, when in fact it's not. It's a small effect. It's just all the studies that have found an estimate of effect size that's closer to what it actually is in the population didn't have enough people to force that effect into statistical significance, and so that didn't get published, so we don't know about it, right? So again, this is why I'm saying it's important to understand this idea of sampling distributions, because all of the statistics that we're working with have some sort of distribution, right? We're doing the best we can. We collect a sample, we calculate statistics, and we say, this is our best guess about what this effect looks like in the population. But again, our effect may be anywhere along this continuum.
I have a question.
Yeah.
On the sample distribution of means, if you only have like 4 people, then you can get it to do like a normal distribution. With this, if you have an effect, if you are identifying an effect and it's not really legitimate, would a sample distribution show, can you do it in reverse, basically? Does that make sense? Or will it end up showing, if you did that, would it end up showing that that's not really a medium or a moderate effect, that it's a more small?
Well, again, remember that this population effect is unknown, right? And the sampling distribution of effect sizes is not normal. It's kind of skewed like that, right? But this is the hypothetical distribution of all effect sizes that could
N
be
equals
50, right? And so this represents the distribution of all effect sizes that could be calculated from samples of size 50 that could be drawn from the population, right? Now, somewhere in there is the mean of that sampling distribution, which is actually equal to the mean of the population effect, right? But this is going to be, let's say, the effect that we're looking at is a small effect, right? That doesn't mean we can't draw a sample of 50 that has a massive effect. Sometimes that's going to happen, right? And chances are this study has more likelihood of being published because it just randomly happened to get a large effect, right? Even though the true population value is down here, right? So what happens is we get this study published, but this Nick's study, Nick's the only person who's found this effect. Everybody gets super excited about it, and they keep trying to replicate it, but they can't. They're like, well, Nick found it with a sample of 50, and I'm not finding it with a sample of 50. Well, because this is probably, with those replications, they're probably getting a sort of a more accurate estimate of the population, but with, or of the population effect, but with sample size 50, this isn't going to turn up as statistically significant, right? So we've got a file for a problem. We've got a bunch of people running studies that don't replicate, and they never get published, and they never see the light of day, right? And so all that hangs out is Nick's study that seems really impressive, but then everybody gets their undies in a twist because they can't replicate Nick's study, which isn't necessarily Nick's fault. It's just that he happened to hit the jackpot, found a large effect, which was nice for him because he got to study it, publish his study. It's not that his effect isn't a real thing. It's just his effect is much smaller than what his study suggested it was, and now everybody else is having a hard time replicating it because everybody else said, well, Nick found it with 50, so I'm going to use 50. What you actually need is 200 actually to get that actual population effect. Okay. So again, thinking about all of the statistics we're running in terms of a distribution and us being blind in terms of whether or not we've got a good sample or a not so good estimate or a not so good estimate. This is where meta-analyses start to become important, right? Because if Nick's one study is out here, but then we go through and we look at theses, dissertations, unpublished studies, and things along those lines, and get a bunch of stuff and say, yeah, looks like there's an effect here. It's just a much smaller effect than what we would assume based on the published literature, because Nick just got an abnormally large effect, and we can find detect abnormally large effects is statistically significant with smaller samples, which is typically what we're working with and stuff. People kind of get a sense, again, sort of bringing this back to thinking about effect sizes and how these work. Okay. Because inferential statistics are hugely driven by the size of our samples, our effect sizes start to help us provide some more meaningful interpretation about the magnitude of whatever effects it is that we're looking at here, right? Other thing to remember too, there are different ways to go through and transition from one effect size to the next, but we have different metrics of effect for different types of analyses, right? And this is confusing. I think this is one of the things that gives people a hard time with effect sizes. If we're talking about p-values, it's the same p-value for any statistical test we run, right? It doesn't matter if we're running z-tests or SEMs. P-value is a p-value, same thing, right? When we're talking about effect sizes, the effect size metrics that we use for different types of analyses are going to be different. And this is a hard thing because then you have to match your effect size with your test statistic, and you got to know what that effect size means and how to interpret it, and so it can be difficult. Now, for meta-analyses, we can sort of convert different metrics of effect into a common metric, like say R, but in general, if you're using you should generally try and use a metric of effect size that matches to the type of analyses that you're running. Okay. So, our effect size for our single sample t-test, raw difference between my observed sample and what I expect under the null, this in and of itself is a metric of effect, right? If I say that I expect people, if I expect students who get their bachelor's in psychology, I'm saying students who get a bachelor's in psychology end up with an income that's equal to sort of the population mean or something like that, right? So students who graduate with a BA or a BS in psychology, I want to know whether or not they make more or less than sort of the average college graduate, right? And so I can say, well, I'm going to go through and I know what the population mean is. So let's have an estimate of what sort of mean income is for university graduates. And then I'm going to go through and I'm going to get a sample of psychology undergraduates. Then I want to see sort of if they make more or less, right? And let's say that I find, it would be nice to people with BAs in psychology, let's say we see that on average we see that we have a difference of $5,000 a year, okay? Okay, well, $5,000, so we find that undergraduates or people who graduate with a BA in psychology make $5,000 more than the average university graduate. Okay, that's a meaningful effect, right? Because I know what $5,000 is. I know sort of what that looks like because we hopefully are all dealing with the same currency. I know what $5,000 is, right? Or I'm working with a weight loss program or something like that, and I just find that people with my weight loss program lose sort of show an average of 10 pounds more reduction than some other program, right? I know what pounds are, right? And so I can make a determination on the reliability of that effect, okay? So if we're working with measures and some sort of outcome that has sort of intrinsic meaning, just the raw difference is a reasonable metric of effect, and then the confidence interval around that tells us something. So we can use that as a measure of effect size. But oftentimes for the types of things that we're doing, right? Angeline, what's a measure that you all use a lot in your lab?
Eating disorder, examination questionnaire, or the PANIS, if you want to talk like.
Okay, so we talk about the PANIS, positive and negative affect scale,
Yeah.
right? What's the range of the PANIS?
Global score?
Yeah.
PANIS? I don't know, we look at some scores usually.
I think it's what, 0 to 40 or something like that, right?
0 to 60, oh yeah, because it's 60 items, 0 to 60.
Okay, right. What is 3-point difference on the PANIS mean? I don't know. Does that have intrinsic meaning to anybody here? No, right? And this is what happens in psychology. A lot of the scales, almost all of the scales, or the vast majority of scales that we're working with have no intrinsic meaning, right? I mean, they're a measurement of something, right? I don't, you know, is 4 or 5 points on the BFI extroversion scale? I don't know. Is that a big amount of it? Is that a big difference? Is it a small difference? If you use that scale a lot, you might say, oh yeah, seems like a pretty big difference. But it's hard, right? Because we're not working with units that have intrinsic meaning. And so what we can do then is we can start calculating measures of effects that are standardized measures, right? And standardized measures are going to put everything in a common metric so that we can start to make conclusions about sort of the magnitude of effect. And for our means-based difference, the Cohen's D family of effects is what we would typically use as our standardized metric of effect size. Cohen's D, people have a hard time sort of with getting off the ground with this stuff. Cohen's D is a Z-score. That's all it is. It's just a Z-score, right? Haley, I tell you I have a Z-score of 2. Is that big or is that small?
It's decent size.
That's decent size, right? Same thing with D, right? Is not different. All we're doing for one sample test, for single sample test, we're taking the difference between our observed minus our expected or our null, and we're dividing that by our standard deviation. Okay, that should be an S, not sigma, because we don't know the population value. But actually, Angeline, can you shoot me an email and tell me to fix that, just so it's consistent? So basically, we're just taking the mean difference, dividing it by the standard deviation, and this is going to give us our standardized effect, right? If I do this, someone who's brave? John, you're looking brave. Actually, I don't know if you're looking brave because you're always hiding behind that computer. So if I'm taking the mean difference, or sort of the difference here, and dividing by a standard deviation, how do I interpret D? Let's say I have a D of 1. What does that mean?
I guess if like it's essentially the same as the z-score.
Yeah, yeah.
It's like your observed mean is like one standard deviation away from there.
Climb over these desks and give you a high five. Exactly. All this is saying, right, if I get a D, an effect size of 1, it's just saying that my observed mean falls a standard deviation above the expected value under the null, right? That's all it means. It's just we were talking about a metric in terms of standard deviation units, right? And so treat this the same thing as I would treat a z-score, right? So if I get a D of 1, I'm saying that we're saying that the population, or the our sample scored on average a standard deviation above expected value under the null, right? And again, if we're thinking about z distributions, a full standard deviation that's a decent size. That's a decent increase, right? Remember, we've got 68% of our distribution falls between a standard deviation above and below, right? What if we got a D of 2? That's massive, right? That's huge, right? I'm saying that my sample scored 2 standard deviations above the expected value under the mean. That's a really big sample, or that's a really big difference, right? And so when we're going through and we're calculating these D family of scores, right? Treat these the same way you would treat a z-score. It's just talking about a difference in terms of standard deviation units, right? And as we start to increase standard deviation units, we can get a sense for how extreme this is, right? I mean, we'll go through some basic benchmarks, but this is the basic sort of interpretation of this effect size here. Other thing we can do is we can calculate an estimate of D directly by taking our T, our test statistic, and dividing by the square root of our sample size, right? For a 1 sample test, I can take my test statistic divided by the square root of n. That gives me an estimate of my effect size D, okay? Now you see asterisks here. It's because I don't want you to provide an estimate if you have the actual information available to you. If you have the mean and standard deviation, just calculate D directly, right? But Kate, where might this conversion come in handy?
When we don't have that information.
Yeah, and when might we not have that information?
You just have a sample.
Okay, so we got the same. So when might we just have a T statistic and a sample size? How about if we're reading someone else's paper, right? This will make you the bane of, as a reviewer, this will make you the bane of people's existence because, oh, I went through and I have a significant effect. I'm making a big deal about my significant effect, right? Well, you didn't give me a sample, or you didn't give me an effect size, so I don't know the magnitude of this effect. And if you didn't give me any means and standard deviations, you should have. But if you don't, as long as I have a T statistic and I know how many people I was in your sample, I can calculate that D by myself. I can say, well, yeah, you got a significant effect because you had 500 people. Your effect size is really, really small, though. And so maybe this needs to start to temper how we're going about and looking at things. So for our class, 99% of the time, this is what I want you to be doing, right? Don't just take your test statistic divided by the square root of n. I mean, this is an easy thing to do, but don't do that because it'll give you slightly different values than this. If you have means and standard deviations, just go ahead and calculate your effect sizes correctly or directly. But if you don't, if you're working with somebody else's paper and you're interested, like, boy, they gave me a test statistic and statistical significance, but they didn't give me an effect size, easy to get it. Okay. Questions on this? All right. Interpretive standards. These are benchmarks. These are loose benchmarks, not to be used as something sent down from Sinai on stone tablets, okay? your assessment of the magnitude of effect should be based generally on your understanding of the research area, sort of what people did. We're going to read hopefully you're going to read a paper, or, well, I'll give you a paper to read. Hopefully you read it on sort of gauging small effect sizes and when these can start to be impressive. But what we have are some standard benchmarks provided by Cont that says, hey, these are generally sort of things we can think about in terms of small, medium, and large effects. Okay, but again, I cannot emphasize these are not bright lines, right? An effect size of 0.49 and 0.51 are not different than one another. They're the same magnitude. Yes, one falls below cutoff for medium, but not by much, right? So use these loosely, right? But in terms of thinking about classic benchmarks, an effect size D equals 0.2, sort of a lower bound threshold for what we might call a small effect, okay? And Cont goes through, talks about this as a reliable difference, but not something that's immediately noticeable just with sort of by looking, right? And so Cont gives an example of the difference between the height of 15 and 16-year-old girls. That'd be about an effect size of 0.2, right? So if I had a bunch of high school women who were 15 and 16, and I looked at sort of, is there a difference in height? I probably wouldn't be able to sort of say, oh, this group is clearly larger than the other, but sort of this would be something that might be consistent with a small effect. A medium effect is something that's noticeable sort of by sort of just general sort of looking. We can see, yeah, there's probably a difference. Corresponding to effect size of D equals 0.5. Evelina, how would I interpret a effect size of 0.5? If I was giving a literal interpretation, what would I say?
That there is a moderate difference.
Moderate difference, so, but be more specific. For a value of 0.5, how much of a difference is that?
Is one the highest that it can?
No, it can be more. What did we say D's were? What D's are like?
The standard deviation.
Yeah. So if we have a half a standard deviation, right? We're seeing about a half standard deviation difference between sort of these two groups. And again, Cont gives the example of the difference in height between 14 and 18-year-old girls. Okay. If we got again some group of women who are 14, group of women who are 18, and we looked at them, 18-year-olds are clearly going to be taller than 14-year-olds. Maybe not a ton, but we're going to be able to eyeball that and see that difference. A large difference in terms of Cont's benchmarks going to be D equal 0.8, right? This is going to be a large, clearly obvious difference. The height between difference in height between 13 and 18-year-old women, right? So this is going to be something that's very clear and obvious, right? But again, you know, Cont in his original text says, do not, under any circumstances, use this as a hard, rigid guideline for things. And of course, we can't do that because we prefer not to think and just take shortcuts and say small, medium, large, right? It's fine if you all, as you're going through in your interpretation, that I want you to give me some sort of sense for general, this is consistent with benchmarks for a small effect, or this is a small to medium effect, or this is clearly a very large effect. So you can use these, be aware of these. These are nice, useful benchmarks, but know that these aren't the end-all, be-all. These aren't sort of bright lines written in the sand for everything and always, right? We might find something. If I found an intervention that could be implemented in a week that significantly reduced rates of homelessness, right? And I found that that was associated with a D of 0.21. Would that be impressive? Hell yeah, that'd be impressive. Why?
Yeah, that's very hard to like.
It's incredibly hard to have any type of impact, right? And so technically I've got a small effect by these benchmarks. But I sure as hell wouldn't be talking about that in my write-up as a small effect. I'd be talking about it as a hugely impressive effect. Because I've done something in a very short period of time that's had an impact on something that's next to impossible to move, right? And so wanting to think about what are we doing, what have we done, and what's the phenomenon in terms of sort of thinking about sort of these benchmarks. Again, for a lot of the stuff, the examples that we run through, you're not all, these are benchmarks, we'll use these benchmarks, but these aren't the end all be all for making a qualitative determination on effects. Okay. Questions on any of this? All right. Wilkinson, going back to Wilkinson, always provide some effect size estimate when reporting p-value, always prevent effect sizes for primary outcomes. It helps add brief comments that place these effect sizes in a practical theoretical context. We must stress again that reporting and interpreting effect sizes in the context of previously reported effects is essentially essential to good research. Okay. It's taken a long time. We've been talking about this over and over and over again, but it's starting to get increasingly difficult to start to publish things in good journals if you're not providing estimates of effect. And really good journals are starting to want confidence intervals around effect sizes. I'll teach you to do both, but it's important, and what we're going to do with these assignments is start to get you comfortable incorporating effect sizes, interpreting effect sizes in a practical standpoint in a way that's meaningful, not just dropping numbers in on people and sort of not really having an understanding of what these mean, how they relate to things, okay? All right. Example, again, we got IQ scores, Flynn effect, same situation as we've gone through before. We'll run through this. How are people feeling about it? Do we want to run through this example? Or are people kind of comfortable with stating null hypotheses, alternative hypotheses, 95% intervals, we'll calculate an effect size for this, hypothesis test, things like that. Are people comfortable doing this, or would it be helpful to walk through another one of these examples?
We are going to do the effect size part.
Yeah. All right, here, I'll run through and sort of calculate this. So we've got null alternative things. We got that, and we can skip over those, right? Calculate a point estimate for the 95% confidence interval of IQ. People comfortable calculating confidence intervals around this? Yeah, okay. And then what we want to do is provide an index of the absolute magnitude of the difference in current scores relative to those observed in 1980. Okay, so what I'm going to do is I've got, so n equals 16, mean score is, oh yikes, 121. That's impressive. And the sum of squares equals 1,600. Okay. What is 6,000? Yikes, what do I do with that sum of squares? Divide by 15, yes. Evelina, why am I dividing 6,000 by 15?
That's n minus 1, so you get the variance.
That will give us the variance, right? So again, sum of squares, when we'll get into this when we start talking about ANOVA, sum of squares is just another metric of variance. It's not a useful metric to look at and determine whether or not it's big or small, but it's just an unstandardized metric of variability. But we can go through and turn that into a variance estimate, right? By taking 6,000 divided by 15, and Evelina, where'd you get 15?
N minus 1.
Right, sample size minus 1, right? So 16 minus 1. And so what is my variance for this sample? 400. Perfect. And what is my sample standard deviation?
20.
What is it? 20. Perfect. All right. We will see where we went through and got that. Again, I got tricky with you, gave you an estimate of variability that's not typically what we would use, but we can very easily move back and forth and get to where we want to be with this. Okay? So, we've gone through and calculated our confidence interval because, well, we didn't, but you can do that quite easily here with this information. But what we want to do is we want to have an index of the magnitude of the difference in current scores relative to the mean in 1980, right? So Emilio, what am I going to do first to calculate my D?
You would take the 121 minus 100.
Perfect. 121 minus 100
And
over
that's
what?
gonna be over 20.
Over 20. Perfect. All we're doing with these effect sizes, we're just calculating a standardized score, right? And it's a standardized score in terms of units of standard deviation based on variability that we have observed in our sample. And what is our effect size that we get with this? Was it?
5.05.
Yeah, 1.05, right? So again, this is, if we, this is gonna be about 20 divided by 20. So again, making sure that you're taking a look and making sure our effect sizes are making sense, all right? And so, yes?
Sorry, I just thought of this. Is
Yeah.
Cohen's D the only measure for effect size?
It's the only measure for effect size for our one sample t-test that we'll use. We'll get into sort of other variations when we get into independent sample tests. All right. Haley, give me an interpretation, a conceptual interpretation of this effect size.
This IQ is about a standard deviation of the mean, so it's somewhat unusual.
Right. Well, we're not making, based on our effect size, we're not making sort of determinations on probabilities and things like that, because that's for hypothesis testing, right?
Okay.
But what we can say is, and you're exactly right, we're going to say, based on sort of the data that we've collected, sort of our sample is scoring about a standard deviation, a little over a standard deviation above the mean value or mean performance on this test for individuals taking the test in 1980, right? And again, this is a population effect, right? I mean, so we're saying that, so we think that the population of people today who would take this is scoring about a standard deviation above what the population score in 1980, right? You don't have to worry about, you don't need to worry too much about your interpretations becoming congested with the use of population. But I would say current sample scored about standard deviation above expected value, expected mean performance on this IQ examination based on when the test was normed in 1980 or something like that, right? And based on Cohen's guidelines, what would we infer about this?
Would it be in between a medium and large effect?
Not quite. What would it be?
It's about 0.8.
Yeah, it's large, right? So if 0.8 is sort of what we conventional cut point for, or sort of criterion for a large effect, we're above
So
that.
that on his interpretations, it's not from 0 to 1. It goes above.
No, right? Because what if our effect size was, or our observed was 140, right? Then we'd add an effect size of 2, right? Effect sizes get really massive, right? Depending on the types of things you're looking at, like sometimes for certain types of treatment outcomes, right? We'll see, you know, if we have people who, I would look at something like social anxiety, it's pretty easy to address with exposure therapy, right? And I took, sort of looked at impact there, I could easily get sort of pretty large effect sizes there. So you got a 2 standard deviation reduction in symptom scores pre and post treatment or something like that, right? But again, thinking about interpreting these in terms of standard deviation units, sort of, and this is something I want you all to be doing when you're making, just like the confidence intervals, you calculate confidence intervals all day long and not know what you're doing. Same thing with effect sizes. I want you guys to incorporate this into, sort of at the end of each one of these, where I'm saying, sort of provide an interpretation, sort of pull all this stuff together. Okay. All right, and so then just as our, so if we wanted to real quickly calculate our test statistic, we would take 121 minus 100, and we would divide that by 20 divided by square root of 16, okay? What's my test statistic gonna be? What's that?
4.2.
4.2. All right. Is that gonna be statistically significant? Yeah, right. I don't know. So someone tell me what my test or my T critical is gonna be for T with 15 degrees of freedom. So, for 15 degrees of freedom, yeah. So 2.131. Okay.
So 121 minus 121.
What's up?
Oh, I see what you did.
Yeah.
Okay.
So this,
never
yeah,
mind.
so the denominator, this is just standard error down here. I just kind of put it all together, right? So our standard error is going to be our standard deviation divided by the square root of our sample size, right? So this is going to be 5, so 121 divided by 5.
I think I gave you the wrong answer.
Okay. What is 21 divided by 5? 4.2. Okay, cool. So, real quick, calculating our test statistics, we get a test statistic of 4.2, right? We have our critical value of 2.131. We're sort of way beyond we far exceeded our critical threshold for this, and so we would reject the null hypotheses. I could run over into GraphPad and ask it what a p-value of 4.2 was, and it's going to be p less than 0.001. That's a massive test statistic right there, right? Okay. People see what I did here. This is just, I took mean difference divided by our standard error. Standard error is just standard deviation divided by the square root of the sample size. Okay. People on the same page, you kind of see what we did here?
So if you're interpreting this one, you wouldn't necessarily say that your sample was so much smarter than the people in 1981, maybe rather infer that the test needs to be updated, or?
Yeah, I mean, and that might be something to go through and talk about, right? So, and this is why we continually have to renorm tests, because, and this is like, we don't exactly know exactly what's going on with Flynn effect. We just know that it happens, right? And so maybe people are getting smarter, or this types of things we asked on IQ tests in 1920 are just kind of common knowledge now. I don't know, right? But again, we want to pull through, and so we would go through here, make an interpretation of confidence interval, right? And so this would be our estimate of the current population mean on the 1980s test, sort of upper and lower bounds. We would say average of this, sort of the current sample scored about a standard deviation above expected population average in 1980. Sort of tested statistically significant, sort of suggesting that evidence for the Flynn effect, given that sort of we have clear evidence of higher mean value on this relative to what we would expect, and this is all kind of consistent with Flynn effect, right? And so that's kind of how we would go through and tie all this stuff together. Yeah.
I just want to correct myself. I gave you the 95% confidence interval, so for 0.01 it's 2.9%.
Oh, okay, cool, yeah, yeah. What is it, 2.947?
947.
For this, sort of inconsequential, given that we've got such a massive test statistic, but yes, thank you for catching on that. So again here, ask for a 95% confidence interval, but then had you run your hypothesis test at alpha 0.01. This is going to be a situation where maybe your 95% confidence interval doesn't contain 100, but maybe your 99% confidence interval might, right? And how might we talk about this, Laura, if we had a discrepancy? So 95% confidence interval does contain or doesn't contain population estimate or the null value, but 99% confidence interval does.
The 99% confidence interval does contain it?
99% confidence interval does contain population or the null value, but 95%, or excuse me, what this would look like is we would get a 95% confidence interval that doesn't contain the null value, right? And so based on that, we would say, based on alpha equal 0.05, we would reject or fail to reject.
If it did contain it, we would.
If it didn't.
If it didn't, we would reject.
We know we would reject the null,
Yeah.
right? But then we run our statistical test at alpha equal 0.05, and we fail to reject because we get p equals 0.055 or something like that. How would we? What would we talk? How would we sort of address that?
I mean, you would talk about the probability of getting that, you would talk about that it would be, I'm sorry, I got myself confused. Because we've gone back and forth that the does and does not contain, so it is in the 95% confidence interval,
No,
but
it's
not.
It's not in the 95% confidence interval, but at alpha equal 0.01, we fail to reject.
Mhm.
Basically, we're just talking about an increase in threshold, right? Again, we're just saying that at alpha equal 0.05, we reject in all hypotheses, right? Is that essentially that our 95% confidence interval is equivalent to hypothesis test at alpha equal 0.05. But if we like crank up the screws, so it's not going to be statistically significant at p less than 0.05 or sort of at alpha equal 0.01, right? And so it would just be a matter of sort of our decision threshold, right? So at 0.05, here's our goalposts. At 0.01, here's our goalpost, 0.001, right? And so you would say we would find, so we would say we find a significant effect or a reliable difference at alpha equal 0.05. However, if we do sort of implement a more stringent threshold of alpha 0.01, this doesn't quite meet statistical significance. However, we have evidence of a substantial effect, right, suggesting a current population scoring about a standard deviation above the expected value in 1980, and so, you know, also noticing that we have a small sample size, looks like our failure to reject at alpha 0.01 is probably going to be more impact of it, more an issue of sample size than nothing to see here, right? So again, this is why we wanted to sort of go through talking about pieces and parts and how all this stuff fits together so that you can make reasonable interpretations, right? Because someone says, you know, you're looking at a paper and someone says, oh, well, we want to be very stringent, and so we set our alpha level at 0.01 because we're doing multiple tests in our sample of 16, right? And say, well, we failed to, so we found that there's no difference between today's performance and 1980's performance because we failed to reject the null hypothesis. Would we have a problem with that conclusion? I would, because saying there's no difference is not an appropriate interpretation of a failure to reject, right? What's an appropriate interpretation of failure to reject, Nick?
That you don't have enough evidence.
Yeah, I'm not saying there is a difference or not. I'm just saying I don't have enough evidence based on sort of the criterion I've tried to say that there's not, to say that there's a difference, right? So saying that there's not a difference is problematic. Two, you set an incredibly high threshold for a sample size of 16, and if I look at my count or at my effect size, I'm seeing evidence of a substantial difference, right? So for you to make strong claims about, oh, we failed to reject, so there's no difference, so we don't need to re-enroll in the test, or everything's fine, we don't have evidence for the effect, is hugely problematic because based on everything you've done, I'm seeing much more evidence that there is something than there's not, right? So I wanted to take some of these types of things into consideration to be able to critically evaluate the types of conclusions people are drawing from their research. All right, how are we doing on time? Time for a break? Probably. Yeah, oh yeah, it is. Okay, cool. Let's go through, take a break, and we'll come back and jump into actual SPSS stuff. Want to go through assumptions of our single sample test, okay? So formal assumptions, we're assuming in order to run a single sample t-test that our outcome variable is continuous, okay? Now, if our outcome is some sort of categorical variable or something like that, we shouldn't be running a t-test. We need to think about something different. But if our outcome is categorical, and we're wanting to compare some mean value in our sample to some external reference value, we're talking about a single sample test, right? Now, oftentimes the types of measurements that we record in psychology aren't technically continuous. Kyle and I just had a discussion about this yesterday in terms of visual analog scales are actually true continuous measures because you can make a mark anywhere along the scale, right? my scale of, scoring this on a 0 to 8 scale technically isn't continuous. What is my 0 to 8 Likert scale actually? What level of measurement? It's ordinal. It's an ordered categorical scale, right? In general, sort of, I'm saying that 5 is bigger than 4, right? But the difference between 5 and 4 and 6 and 7, there's no, right? And so generally this doesn't cause too big of a problem with our t-tests, but it is something to keep in mind, right? Particularly if we start to get weird distributions. So rule of thumb, ordinal scale with 5 or more values can treat as continuous, but again, sometimes people get more upset about that than others, but something to keep in mind. Big thing, observations are independent, okay? So if I give you all a personality measure, Amelia's score needs to be different than Laura's score, needs to not be related to Layla's score in any way. This is a methodological thing. We want to make sure that scores are independent assessments of one another. If we start getting correlations between if Laura's score is to some extent dependent on Haley's score, then that's problematic, and we've got big issues in terms of our analyses. So continuous outcome, observations are independent, and this is a big one, okay? Distribution of sample means for the population is normal, okay? Kate, tell me what do I need to in order for to make an assumption of that the distribution of sample means is normal? What are the 2 conditions under which distribution of sample means becomes normal?
A larger sample size.
Large sample size, and what else? Anybody help her out? What's the other? Large sample size is the big one. What's the other thing? Yeah?
Is it something to do with random sampling?
Not random sampling, not random assignment. If whatever I'm measuring has a normal distribution of the population, then if I'm looking at height, right, I don't have to have a large sample of height in order for the distribution of sample means to reach normality, because height is generally has a normal distribution, or expected to have a normal distribution of the population, right? So if whatever I'm measuring has a normal distribution of the population, or if I have a large sample, or both, then I'm expecting my distribution of sample means to approach normality very quickly, okay? So Nick, what's my assumption in my t-test about the distribution of my observed data?
The t-test isn't positively skewed?
Well, but the not skewed, kurtotic, that's a t-distribution. Technically, I don't have an assumption about the observed scores in my sample, right? The assumption of the test involves the distribution of sample means, not my actual sample, right? So is it okay for me to have a funky distribution in my observed sample?
Yes.
Maybe, right? It kind of depends. Now, if I've got a nasty distribution in my sample with a bunch of outliers and weird stuff, and I've got a sample of 10, then probably no, that's not okay, right? Let's say I'm measuring heroin use in college students, and I've got a sample of 10, and my distribution of observed scores is ugly, then I've got a problem, right? Because 1, I'm not measuring something with a normal distribution in the population. 2, my sample's tiny, and so I have no expectation that that distribution of sample means is going to approach normality at all, right? But let's say if I'm using, I don't know, Kate, do people use heroin more often or cocaine more often? Cocaine, okay. Let's say we're talking about cocaine use in college students, so maybe, or let's say amphetamine use, or so stimulant use, something like that. Still probably not going to have normal distribution, right? But if I've got a sample size of 50, right, even though my distribution of stimulant use might be skewed, I'm not too worried about it, because the distribution of sample means with a sample of 50 should approach normality fairly quickly, okay? So this is important. We're still going to go through and evaluate the distribution of scores. because we want to know what's going on in our data, and if there's weird outliers and things like that, we want to make sure that we're addressing those properly. But what we find is our analyses, our sort of basic t-tests, our means-based analyses, generally robust to violations as long as our sample's about 30 or more-ish, okay? So formal assumptions, continuous outcome, independent observations, and the distribution of sample means is normal, okay? Informal stuff, the data don't contain outliers, right? This is a means-based test. If I've got scores that are way too big or way too small, particularly if I've got a small sample, that starts dragging my mean all over the place, right? So we're gonna identify outliers as extreme scores in our data, but as we're going through, and again, I'm gonna sort of beat you guys up on this, right? Like what's an outlier is a subjective, it's kind of a judgment call, right? Now, if we've assessed income and Bill Gates is taking a correspondence class through the university and he gets captured in my sample, that's not a subject call, or that's not a subjective issue. That's something that's categorically different type of thing going on, right? But when we're going through and taking a look, again, sort of forcing you off these rules of thumb, like, oh, at this level it's an outlier, at this level it's not. No, I don't know. It depends a lot on my sample size, what I'm measuring. Are these scores an expected part of the distribution? A lot of different things start to go into what I do or how I might identify an extreme value, okay? So what I don't want you to do is just say, oh, case number 43 was an outlier. Well, based on what? Tell me what your criteria was for identifying that as an outlier, right? And just because it's an outlier doesn't mean it's necessarily problematic. You could have a score that's quite a ways out there, right? But if we've got a sample of 100, how much of a difference is one score going to make in a sample of 100? Probably not that much, right? Particularly if we're using something that's that we typically use in psychology, which are some sort of measure, right? If I give Nick a BDI, Nick can only score so high on the BDI, right? If he taps the whole thing out, he's going to have a score that's much higher than maybe the rest of the sample, but it's not like something like income, where I could be several orders of magnitude larger and start dragging things around. So one of those things to start thinking about in terms of how we're thinking and qualifying this stuff, okay? Questions about assumptions in the t-test, okay? And the thing that's important to recognize here, folks, is that, and why this is important and why this impacts our inference, again, thinking about distributions. Let's say this is T with D degree of freedom 30, okay? So this is the distribution of my T statistic with degrees of freedom equal 30, okay? This is the distribution of my T statistic with degrees of freedom 30 as long as these assumptions are met, right? If I start to violate these assumptions, the distribution of my T statistic with degrees of freedom 30 tabled in there, that's not the distribution anymore, because these are the rules of the game. And as long as we're following the rules of the game, this is my distribution. And if this is my distribution, then I can just start assigning p-values to stuff. But as soon as I start violating some of these things, now all of a sudden, I've got a distribution of my T statistic that doesn't look like this. It's something else, and I don't know what that something else looks like. And if the distribution starts to change shape, that starts to throw off my ability to assign probability values, and now everything kind of goes out the window, okay? So this is why it's important that we go through and assess our assumptions, because our sampling distributions are based on certain criteria. And if we violate those criteria, now we've got a test statistic that follows some distribution. I just don't know what that distribution is. If I don't know what the distribution is, I can't assign a specific probability value for finding a value of some level or higher, and then all of a sudden my statistical inference starts to fall apart. So this is why assessing these assumptions are important, but then also knowing and recognizing sort of what violations are going to cause us some problems and which types of violations aren't. Okay. Questions about this? Okay, cool. So you should, pull out your handout that is, what are we calling this? Your single sample T screening. Okay. And go through on your computers and pull up your data set that's MBA t-test. Okay. So what we have here is a small sample, 27 individuals, and what we've done is, so these are individuals from the community who have experienced a significant motor vehicle accident and are experiencing some difficulties with anxiety and have come in and received an assessment. Our CAPS is a clinician-administered PTSD scale. This is an interview-based measure of PTSD. Scores range from 0 to 136. And so this is our interview-based assessment of post-traumatic stress. And so we'll see here, we've got things that you need to worry about as our subject numbers, PTSD final, right? 0 equals no PTSD, 1 equals PTSD. Haley, what can we determine based on this sample?
Could you repeat that?
I said 0 equals for PTSD final, 0 equals no PTSD, 1 means meets diagnostic criteria for PTSD. What do we know about this sample?
They have PTSD.
Everybody in the sample has PTSD following motor vehicle accident, right? And so what we're going to do is we're going to run a test. So we've got an assessment procedure, and we're bringing people in after car accidents, and we're running our running people through CAPS. But eventually, what we want to know is our sample representative of some normative sample of car accident survivors, right? So what we want to do is we're going to go through and compare our data against a reference value to say, so are our participants kind of in the expected range based on certain parameters, okay? And so we're going to use a one sample t-test to do that. But before we do that, we want to go through and we want to make a determination on whether or not our CAP scores meet the underlying assumptions of our single sample t-tests, okay? And so for this problem, we're just worried about our CAP scores. But what we're going to do is we're going to start by taking a look at characteristics of our distribution. Okay, so we're going to go to descriptives. So we're going to analyze descriptive statistics, descriptives, and we're going to put our total score for CAPS. We're going to put it in our box here. Then we're going to click this little box that says Save Standardized Values as Variables. What this is going to do is this is going to calculate z-scores for everybody in our sample. Okay, we're going to use this to take a look at extreme values. And then I'm going to go to Options, click Options. I'm going to ask for skew and kurtosis and skew values. Okay, everybody follow me up at this point? I'm going to hit Continue. All right. Then I'm going to hit Paste. Right? This is my syntax file. Okay? This is where I'm going to keep a log of all my commands so I don't have to keep running down through a stupid pull-down menu over and over again. This also gives you a record of what you've done for your analyses, so lets you go back through and take a look at stuff. You will need to save syntax files. Anybody here work with syntax files? Familiar with syntax files? Emilio, John, a little bit. Anybody else? Okay. All right, Laura. You'll become. No.
Not loud.
Okay. You'll start. This will start to become sort of second nature to you. Okay. One thing we're going to do in this demonstration, and again, this is just nice in terms of having a record of what you've done. In your syntax file, you can go through and start writing comments, and so anything that starts with an asterisk is going to be a comment, right? So these are notes that you can write to yourself so that you can sort of keep track of what you did and what different things mean. So for this, I'm going to say, looking at distribution of caps and calculating z-scores. Okay. Now, one thing in this, you'll need to make sure that you have a space in between your comments and your command line, otherwise it won't run it. But basically what we're doing is we're running descriptives for caps total. This is going to save z-scores based on our sample here. And then these are the statistics that are going to be provided to us here. Okay. Questions on what we've done? All right. Then what we're going to do is we're going to go through, and highlight our command, and then we're going to run this. Okay. That little green arrow is going to run, and this is what we've got. Okay. So, what are we looking for? Amanda, what are we looking for? What can we glean from sort of this initial look at our descriptives here?
Your mean's just your mean.
Okay, so I'm going to go through, take a look at my mean. One thing we want to do when you're going through and screening, first thing to look at is sort of missing values and plausibility. Okay, always want to look at missing values, plausibility. How many cases do you have in the sample? Just looking at the actual data. 27. We've got 27 scores. No missing caps data, right? So this is important. So we want to take a note of that. Say no missing scores. Also, looking at this min and max, right? Things happen all the time where things get miskeyed in, something happens, right? Always want to check the plausibility of your scores. Emilio, what is, based on your handout, what's the accepted, or what's the range or minimum max value for caps total?
I think I have the wrong.
Just on your handout here.
0 to 136.
0 to 136. So I go through, my minimum value is 37, maximum value is 92. Tells me that all my data, that all my values are in range, right? Always want to check this because one, we have sometimes RAs that sort of just miskey stuff. Sometimes this is what I do for missing values in our lab. I enter, if I have a missing value, I'll enter 999 in there, and that's just a missing value code. That helps me because that 999 tells me that we didn't collect a score for this person. Because if it's just blank, I don't know if we have a missing score or if someone just didn't enter it, right? If there's a 999 in there, that says to me that, yep, we actually are missing this score. But if I don't tell SPSS that 999 is a missing value, 999 will come up as a value here, and I need to make sure that I go through and catch that, right? So always, first thing we do in the screening, one, make sure that we're not missing any values, and then two, make sure that our scores are within range, right? But both of those look okay here, right? Other thing we're going to be looking at is our skew and kurtosis indices. Anybody remember what kurtosis?
One of them's like 2 or something.
Yeah, both 2. Skew and kurtosis less than 2 is often used as kind of a guideline for sort of what's reasonable in terms of skew and kurtosis values. But again, this isn't a hard rule. One, if you have a skew of 2 when you graph those data, it's going to look incredibly skewed, right? And so you don't want to say, oh, it's about normal when it's clearly not, right? Other thing too is we want to go through and take a look at our sample size. What is our sample size looking here? Layla, are we happy with this sample size?
It's kind of small.
It is kind of small, right? I mean, I guess, right, this is hard data to collect, so it's better than something that would be smaller, but it's still, at the end of the day, a fairly small sample, right? So we know that we've got a small sample, but Our skew and kurtosis values are reasonably close to 0. So again, just based on these statistical indices, Haley, are we too concerned about non-normality, or should we have immediate concerns about the normality of our data? No. Do we even have normality assumptions about our observed data for this test? No, right? We have assumptions about the distribution of sample means, right? But again, if we started to get something really wonky with a sample of 27, that would start to make me nervous, right? But at least based on what we've done here, this is looking okay. All right. Questions on what we've done up to this point? All right. So distributions aren't looking too bad, I guess, at least at this point. Well, what I want to do is I also want to go through and take a look at graphically what's going on. So I'm going to go to graphs, go to chart builder, and it'll ask you to do some stuff. You say okay. What I'm going to do is I'm going to go through, I'm going to select histogram, and I'm going to grab this, I'm going to pull it up here. Okay. This is saying I'm ready to draw a histogram. Then I'm going to select caps total and drop it down into that box. Okay. Now there are another bunch of other different types of things that we could do with this. We won't worry about it. But again, we're going to go ahead and we're going to hit paste. Okay. And here you'll see that you now have your commands for graph stuff. This is never anything that you would ever just come up with on your own. This is something you're going to want to always go down through and pull out from your pull down menu. But now that you've got it saved to your syntax file, you can very easily go through and just run this. Okay. But before we do, we're also going to go through and we're going to go back to graphs. We're going to chart builder, and we're going to ask for a box plot too. Okay. And what we're going to do is we're going to take this box plot, pull it up here, and same thing. We're going to keep caps total score. Oh, looks like it was already there. All right, so we're going to get both a histogram and a box and whisker plot for cap stuff. Okay, and then we're going to paste that here. And maybe what I want to do is I want to go through and I'm going to say, oh good, requesting graphical distributions or something like that, just so I know kind of what's happening here.
Is the program sensitive to a certain amount of asterisks or no?
No.
Okay.
Yeah, I don't know what they're. All right, so we've got our graphs. Going down through, run this, and here we go. Okay, Amanda, what am I seeing based on sort of this histogram of cap scores? Am I seeing any concerns?
It's not a very normal distribution, and you have some gaps.
Well,
It's
for
not
20
that
for
bad,
27 people,
but it's
that's,
not bad. But
yeah. I'd say that's pretty good, right? I'm not gonna crab at that distribution too much. We'll see with 27 people, we'll see a lot worse than this. But sort of kind of looks like people are generally kind of falling around this middle piece, and some people a little lower, some people a little bit higher, right? But if I was describing this this distribution, I'd say it's sort of anybody done like neuropsych work before, neuropsych assessment stuff? You might call this unremarkable, right? This is what your doctor says if you come in, you're fine with muscle executive, you know, sort of orientation, blah blah blah, unremarkable, or health history unremarkable if you haven't had weird stuff going on, right? This looks pretty good. Okay. What about our box and whisker plot? Layla, tell me, what is this represent on my box and whisker plot?
Sorry, can you point to it again?
Yeah, this guy right here.
That's our
What is it? Median. Remember our box and whisker plot is this is median-based statistics. Okay. So this is my median. What is this?
our standard year.
No. So what's this and what's this? What do the bounds of my box represent?
Q.
What's that?
Interquartile.
Inter-
Interquartile range.
Okay, this is my interquartile range, right? So this is my third quartile, this is my first quartile. First quartile is my 25th percentile, right? 25% of my scores are falling below here, this value. This is my my third quartile or my 75th percentile. 25% of the scores are above. This interquartile range, remember, is my middle 50. So the 50%, half of my scores fall somewhere in between whatever this value is and whatever this value is. This is my median value here. Okay. Haley, can you remind me what are the bounds of my whiskers here?
It should be your lowest and highest values, your range, right?
Within
I don't know what you're.
you're almost there. What's missing from this? Okay, now that's standard deviation. 'Cause standard deviation, that's mean-based stuff, and this is all median-based statistics. Because this is my highest value and this is my lowest value right here, right? So whiskers, so my upper and my lower whiskers, this represents the most extreme value within 1.5 times the interquartile range. Okay, and then values falling beyond your whiskers, these are values that are going to be values that fall beyond 1.5 times the interquartile range. So we've got 3 scores up here that are falling beyond 1.5 times the interquartile range, 2 values below falling beyond the interquartile range. If we get something that's falling beyond 3 times the interquartile range, those start to pop up as asterisks in SPSS, right? So wanted to make sure that you can go through, describe kind of what's going on with this, right? What overall might we say, Evelina, about sort of this box plot?
So there's like a lot of outliers for just 27 people.
Okay. And I can see how one might arrive at that assumption. But again, this is where we want to be careful in terms of what we're calling outliers, right? I wouldn't call an outlier anything that comes up as something that falls beyond 1.5 times the interquartile range, right? Again, does it look like we have too many outliers here? Probably not, right? So what we want to do is we want to be very careful. So yeah, these are more extreme values relative to the distribution than maybe some other ones. But we could say we have in this graph, we've got 3 values falling above 1.5 times the interquartile range, and a couple values, cases that are falling more than 1.5 times below the interquartile range. But overall, based on these 2 distributions together, do we have too many concerns about sort of the distribution of these scores? Probably not, right? I mean, median's right there in the middle. Sort of this looks like, sort of a little bit, this whisker's got a little bit of a sort of drag down towards the bottom, but things overall look pretty even and Steven, okay? So between our values for skew and kurtosis, our histogram, and our box plot, do we have in these data any clear concerns about violation of our assumptions of distribution of sample means? Probably not, right? And this is good because this is a pretty small sample, right? Now, so sample small, I wouldn't say the distribution of sample means is going to approximate normality super quickly with a sample of this size. Now, are CAP scores normally distributed in the population of people who have motor vehicle accident PTSD? Maybe-ish. I mean, so if we're just talking about people with PTSD, sort of that, but I don't expect you to know all of that business. I would say probably not terribly skewed, right? This is probably about what we would expect. But here, we don't have clear concerns about missing values, implausible values, and our distributional assumptions look pretty reasonable based on what we looked at here. Okay. Last thing we're going to do is I'm going to go through, so you notice that when I requested my descriptive statistics, there's this save command here, right? What that save command is going to do is it's going to, in SPSS, it's going to create a new variable that's going to contain Z scores for whatever variables are examined in your descriptive statement. Here we just had cap scores. So what it did is we've just calculated z-scores for our caps. Now, do we need to look at the distribution of z-scores? What do you think, Laura? No, why not?
Because we checked out the distribution.
Yeah. Distribution of z-scores are going to be the exact same as the distribution of my regular scores. That didn't change the shape of the distribution at all, right? It just turned them into standardized scores. But what I am going to do is I'm going to go to Analyze. You go to Descriptive Statistics. I'm going to hit Descriptives. And this time I'm going to ask for Descriptive Statistics for my z-scores. And what I'm going to do is I'm going to turn off Save Standardized Variables because I don't need to create z-scores in my z-scores. That's redundant. And in Options, I don't need to know skew and kurtosis because I already know what skew and kurtosis my distribution is because we've already looked at that. And then I'm going to hit Continue, and I'm going to hit Paste. Okay. Now, so here, you'll see this is my command for my descriptives for my z-scores. What you'll do when you start to get more familiar with this, I could have just taken this, and I know that SPSS just puts a z in front of anything it calculates as a z-score. I know that I don't want to save z-scores of my z-scores, and I know I don't need skew and kurtosis values. Get rid of that, and then I'm right to where I started before. This, as you start to get more and more used to SPSS and using these syntax files, it starts to become easy because you'll have basically a screening file. This is kind of the steps I go through. And what you can do is instead of just running everything through the pull-down menu, you can just start typing in variable names for things you wanted to go through and take a look at. We're not there yet, but we'll get there eventually.
Do you have to maintain the period at the end to show the end?
Yeah,
of the
you do. For this programming language, it needs that period there.
That's your, okay.
Yeah. All right. So what we're going to do is oh yeah.
Sorry, I kind of missed how you made the new column for CCAP's total scores on the actual data set.
You already did that. So if you go through up here, this save, right? So when we go through and when you go analyze descriptives right there, if I hit save standardized values as variables, it's just going to create a new variable with z-scores. Okay. So, but we've got that done. Go through, run this. Okay. So John, what am I looking at here when I'm asking for descriptive statistics for my z-scores?
Say that again?
So I asked for the descriptive statistics for my z-scores. What's of most interest to me here?
The minimax.
Exactly, and why the minimax?
Because that'll tell you for the which score percent scores are fall below
Yeah,
this
right.
one.
It's telling me, so that in terms of standardized terms, so it appears here, I don't care about mean standard deviation, this is just telling me that it created z-scores, right? But what I want to do here is take a look at my minimum and my maximum. And so it looks like my lowest score is close to a little under 2 standard deviations below the mean. My high score, a little over 2 standard deviations above the mean, right? And so what we can do is start using this as a metric for if I have extreme values, how extreme are they from a means-based standpoint, right? And so again, because these are z-scores, we can interpret these as standard deviation values. If I wanted to, I could start setting cut points, right? So I could say, 1.96 would be a z-score that would just be associated with p equal 0.05, right? 2.58 would be p equals 0.01. 3.29 would be p equals 0.001 in terms of like thinking about the magnitude for cut points, right? But you want to be careful with this because this starts to depend on the size of your sample and sort of thinking about things, right? So here, like if we said we wanted to call extreme scores scores that fall 3 standard deviations from the mean, right? So we're looking at a z-score of 3, or if we wanted to push it, and so a z-score associated with a p-value of 0.001, you say a cut point of plus or minus 3.29, right? But again, if you're going to use those cut points, we want you to describe sort of like, oh, this is what I'm using my cut point, so give me a rationale for why. Here, we've got on the low end something a little under 2 standard deviations, at the high end a little over 2 standard deviations. But again, based on my graphical distributions, things along those lines, am I too worried about outliers based on this? No, right? I would say, you know, it appears that if I go through, so this is another thing, click on z-score caps total there, and then right click and hit sort, and then they'll just run these up. So I might say in this that case 15 has a z-score that exceeds 2 standard deviations, that's above 2 standard deviations above the mean, right? So this is associated with a cap score of 92. But at the end of the day, are we comfortable moving forward with our statistical tests without concern of gross violations of our underlying assumptions? Things are looking pretty good here. Okay. So we've gone through, we've taken a look for missing values. We've taken a look for implausible values. We've taken a look at distributions in terms of skew and kurtosis indices. We've taken a look at our histograms, and we look at our box plots, trying to go through and take a look at stuff. We've looked to sort of quantify our extreme values in terms of z-scores. All of this is looking good. It won't always, but here it's looking pretty good. We would say, okay, we can go through and proceed without too much concern here. Okay? Questions about this process? All right, so all of this is laid out here in your handout. Sort of the same commands and things like that. But again, what I would encourage you to do is save these files, because it's going to provide a nice template for what I need to be doing, going through and taking a look and checking for these different types of tests. Okay. All right. So that was a whole lot of work for something that's actually going to be pretty straightforward. Okay. So what I want to do now, pull out your single sample t-test. So to this handout here. And what we've got is let's say from the literature, we've got normative scores for individuals with and without PTSD following a motor vehicle accident. And we're using these as reference values from Coffey et al. 2006. And so this study found that average CAP scores for accident survivors without PTSD, average CAP score was 24.7. For those with PTSD, the mean score was 70.1. Okay, and so let's say that we're wanting to see how our sample ranks against sort of these reference scores. Okay, so what I'm going to do is I want to see, so does my sample have PTSD or not have PTSD? They have PTSD, right? And so if I've done a good job of diagnosing PTSD, my sample with PTSD should probably have larger CAP scores or higher CAP scores than single sample t-test. So what we're going to do is we're going to go analyze and compare means, one sample t-test. Okay. And then we're going to be interested sort of what the variable we want to test is our CAPs. And then we want to put a test value. Okay. Amelia, what's my test value here? If I want to see whether or not my sample that I've said has PTSD, whether or not they have significantly higher CAP scores than a reference sample without PTSD.
Wouldn't it be the PTSD or?
I don't know if you have. So what's my reference value?
1.
What's up?
It would be 0, 1.
Oh no.
Oh, yeah. 1. No.
Okay. is it gonna be reasonable for me to test whether or not at my mean value, my CAP score is larger than 1? No, that's not gonna be.
Oh. Yeah, it'd be 70.1.
Okay. So someone help us out. What is it?
Would it be 24.7?
It's gonna be 24.7, right? So 24.7 is my null value, right? So I wanna see, I've got a population that, so I have a reference, we're saying a reference population. This is a population of accident survivors that don't have PTSD. And their average CAP score is at 24.7, right? It's not 0, they're gonna have some stuff, but they don't meet diagnostic criteria for disorder. And so for individuals who've been in bad car accidents, who don't meet PTSD, their average CAP score is 24.7, right? So think about that. My reference population under the null is the population of accident survivors without PTSD. What I'm saying is I have a different population. I'm saying I have a population of accident survivors with PTSD. And so what I want to do here is I want to see whether or not my sample is representative of a population that has higher scores than sort of the population without PTSD. Okay?
On
Yeah.
this handout, the second line down is the mean of 70.1. Is that the population mean?
Don't worry about that quite yet.
Okay.
Okay?
Sorry.
So we're on the first t-test. So we're on the one that says 24.7.
Got it.
Okay? So what I'm going to do is I'm going to go through, put in my test value, and then I'm going to hit paste. And so I can go down through here, double asterisk. Oops. We'll say comparing sample to ref pop without PTSD. Okay. I'm going to go through, highlight that, and I'm going to run it. Okay. And this is what I get. All right, so walk me through this. Layla, what's going on with up here?
Our mean score is 62 with a standard deviation of 13.4, and our standard error mean is 2.5.
Yeah, right. Nice. SPSS just popped this stuff out. This is all stuff that I could do. Nick, if I wanted to calculate a confidence interval around 62, could I do that? Yeah, right. I mean, I got my standard error right there. I mean, I have to figure out what my critical value is. I can do that pretty easy, right? But I actually don't have to because, well, I want to be careful here. I could calculate a confidence interval around my mean estimate of 62 right here based on this, right? But if I go down through and I take a look at my one sample test, Kate, what's going on with my one sample test here? What's my test statistic? 4.4, yeah, 4.2. For t-values, go ahead and just report those to 2 decimal places. P-values to 3 decimal places. But 14.36, that's big. That's really big, right? 26 degrees of freedom, and my significance is going to be p less than 0.001. Don't enter p equals 0.00 because your probability is never 0. But it's going to be p less than 0.001, right? So Amanda, do I reject or fail to reject the null hypotheses?
You reject.
I reject the null hypotheses, right? And I would say, based on my statistical tests, we have evidence to suggest that average CAP score in the population that we're pulling from is greater than our reference value of 24.7, right? And then we have a confidence interval here. Evelina, what's this confidence interval around?
The point estimate of 62.
Is it? No, it's not, right? Because 62 doesn't fall in there, right? What is this confidence interval around? What is SPSS giving you? What's that?
37.3.
Yeah, it's the difference, the confidence interval around the difference, right? So wanted to be careful. So what we could do is we could very easily calculate a confidence interval around our mean estimate of 62, right? And this would give us a range of plausible values for the average cap score in the population of motor vehicle accident survivors in Buffalo. That's where we were doing this stuff, right? Now, my reference values are going to be coming from a population that's different. This is from some other place, so technically it's a different population. But what I could do is I could calculate a confidence interval around the average cap score in the population of Buffalo accident survivors with PTSD, right? Or, alternatively, I could go down through and interpret this as, here's my point estimate for the difference between my sample statistic, or my sample mean, and the reference value. And then this is the confidence interval around that difference, okay? And so what I would say here is I would say, so based on the data that I've collected, I'm estimating that accident survivors with PTSD are scoring about 37.3 points above average values for the reference sample on the CAPS, and reasonable or lower bound and upper bound estimates for the true population difference is going to be anywhere from about 32 to 42.6. Okay, so we're talking about slightly different things. This is a confidence interval around the point estimate of the mean. This is a confidence interval around the difference. You could use either one of these to talk about this, right? Here, we're just talking about the raw, so the actual point estimate. Here, we're talking about confidence interval around the difference. This is the same standard error used to calculate this confidence interval as it would be here, so they're interchangeable.
But the samples that would fall in that lower confidence interval, that's people that do not have PTSD?
Nope, this is the difference, right? So
Right.
my point estimate of the difference between people who have PTSD and people who don't, or accident survivors who have PTSD and who don't, is about a 37-point difference. Pretty big, right? But again, we don't know sort of the actual population difference probably isn't exactly 37.
Got it.
Lower bound, anywhere from about 32 to 43 is going to be a reasonable estimate for the true difference in my population relative to this reference value.
Got it.
Okay, people kind of see where that's coming from.
How would you calculate that by hand? Is that just the
Calculate.
mean difference?
Yeah, so we would take this the mean difference, right, and then we would say so mean difference plus or minus whatever our critical value is for 26 degrees of freedom multiplied by our standard error. So this interval estimate, the width of this interval estimate is going to be the same width as sort of what we would get up there. It just depends on how we want to talk about it. Last thing we might want to do is maybe we want to calculate an effect size for this, right? And so what I'm going to do, I'm going to say D equals 62 minus, what's our reference value? 24.7 divided by what? Okay, that's my standard error. That'll give me my test statistic. For my for my effect size, what I want to do over there.
13.499.
Yeah, 13.499. Okay. What's my effect size? $2.76. That's massive, right? And so I would say here that my sample of accident survivors with PTSD are scoring about 2 3/4 of a standard deviation above the average score in the reference population without PTSD. Okay? And so again, what we would do is we can use sort of output that's provided here to go through. We can run our statistical tests, right? But we also got our confidence interval. We can calculate SPSS can calculate effect sizes for us. We have to do that by hand. But we can go through and with the information provided here, very easily and quickly do this. Okay. Questions about this? We could also go through with our syntax file, right? And let's say we wanted to see whether or not our sample or our PTSD scores in our sample are similar to individuals, accident survivors with PTSD based on that reference population. Okay. So Nick, what would be the value under the null if we want to compare our survivors with the reference sample with PTSD?
70.1.
70.1. 70.1, right? And again, this is a nice thing about using your syntax file. We can just go through and copy and paste and just change the reference value. Go through and we can run that. And boom. And Nick, what's our conclusion based on our one sample t-test here?
Reject the null.
Yeah, we were rejecting the null, and sort of what's going on here?
You're significantly lower.
Yeah, right. So it looks like our it looks like CAP scores in our sample that we've collected, at least our sample of 24, our sample is reporting scoring statistically lower scores than the population from which the reference value was drawn, right? And so maybe this means that individuals with motor vehicle accident related PTSD in Buffalo is technically a different population than maybe where their reference values were coming from. But it looks like, at least based on these data, we're scoring systematically lower than wherever the reference population was coming from here, right? And so again, we've got our mean, we've got our standard error. We calculate standard confidence interval around our mean, but that's going to be the same thing we did up there, right? This is going to be a confidence interval around our difference of, we've got a difference of 8 points on this. But again, if we want to calculate an effect size, we're going to go D equals 62 minus what? 70.1, right? Over, and again, 13.499 is going to be our standard deviation. And so what's our effect size here? What is it?
56.8.
One more time.
56.8.
Oh, probably not 56.8. Negative 0.6? Okay.
That's where we're at.
Negative 0.6.
-0.60004.
Oh, okay. So just the 3 decimal places.
000.
Oh, negative 6. Oh, that's convenient. Okay. I get weirded out when we get just 0 decimal points here, right? So Evelina, tell me how we would interpret this effect size here.
You would say that your sample falls about maybe a little more than half.
I'd say 6/10. Yeah. I mean, you could reduce 6/10, but 6/10 is easy. We say our sample is scoring about 6/10 of a standard deviation below the reference sample so that we're using as a comparison, right? So here, kind of an interesting thing, right? It looks like, sort of based on what we've done, that our sample of people who we say have accident-related PTSD are scoring reliably significantly higher on the CAPS than our reference group without PTSD, right? So that's good. It's saying that we're not just saying people have PTSD when they don't. Now, we also see that participants in our sample are scoring over the population from which we're drawing from. Looks like it's scoring significantly less than sort of the reference value that we're using. But we're looking at a 2 3/4 standard deviation above our reference value without PTSD, 6/10 of a standard deviation below. This is a massive effect size. This is sort of in between the sort of the medium and large effects, right? And so what we might do then is think about, what does this mean for our data collection, our samples, sort of the population, sort of do we see regional differences in terms of some mental health outcomes or things along those lines. Some different things that we might want to go through and start talking about. Okay? All right. Thank you, folks, for hanging in there with me. How are people feeling about sort of this process? Okay? All right. We're making good progress. We'll pick up with, finishing up with